Bayesian rules in the Bayesian disaster. My name is Stefano Barone and I am a professor of statistics at the University of Palermo, Italy. Before analyzing the case in question, it is necessary to make a brief and quick premise on the main rules of probability calculus. I give some fundamental definitions. An event concerns a situation that we can define as possible and uncertain. It is the result of a chance. The event is distinguished from the fact that is believed to be true as it happened with certainty. An event admits its negation, a fact does not admit it. The probability refers to an event E and is denoted by PR of E or P of E. The probability is a primordial and congenital concept. It is a concept that matures in a human being from its birth. The concept of probability cannot be defined exhaustively. Each definition of it is repetitive and can be contradicted. Nevertheless, since the recognized value of the concept, even for scientific purposes, the given definitions are classified into three categories: classical, frequentist, and subjectivist. Classical definition. The classical definition, the probability of the occurrence of an event is the ratio between the cases favorable to the occurrence of the event and all the equally possible cases. In the frequentist definition, the probability of the occurrence of an event is equal to the ratio between the cases in which the event historically occurred and the total number of cases in which the event could have occurred. In the subjectivist definition, the probability of the occurrence of an event is a degree of confidence that a consistent individual or human subject places in the occurrence of the event on the basis of his or her state of knowledge. Whatever definition is adopted, the probability must be calculated with a method that correctly uses all the information available, avoiding inconsistent evaluations. Complementary event. The complementary event of an event E is the negation of E, and it is indicated by E with this sign that is read as E negated or E denied. E and E denied are incompatible events because the occurrence of one excludes the occurrence of the other. It is read as E intersection of E denied is equal to the impossible event. The sample space, if we join an event E with its negation, E denied, we obtain the so-called sample space S. The union of E and E denied is equal to the sample space. The sample space represents an event that is certainly true, as at least one of the events included in it will certainly occur. A probability 1 is attributed to the sample space, while a probability of 0 is attributed to the impossible event. To any other possible event E, a probability is a fraction of the probability of the sample space. So the probability of an event E lies between 0 and 1. The Venn diagram. The Venn diagram is a useful tool for representing events and the probability associated with them. The rectangle, denoted by S, represents the sample space and the set A, the genetic event. The probability of an event is proportional to the size of its area in relation to the area of the rectangle. Elementary operations on the events. If the event A happens, the event B happens too. This is the symbol that we use. A is contained in B, and also graphically we see that the event A is contained in B. In this case, B can occur even if A does not occur. There's a portion of B outside A. Coincident events, if A is contained in B and B is contained in A. Impossible event cannot be represented in the Venn diagram. Complementary event is represented as follows, as the green area, which is outside the event A. Union of two events, A and B. It means either only A or only B or both occur. It is represented as follows in the Venn diagram, as in the yellow area. Concomitance of two events, A and B, that means that both events occur. In the Venn diagram, it is the intersection of the two sets, this one. Incompatible events. Two events A and B of a sample space are incompatible if there is no possibility of concomitance. They are represented as follows, as two disjoint sets in the Venn diagram. Intersection is the impossible event, and the probability of the intersection is equal to 0. As we have already seen, the union of E and E denied is equal to S, and intersection of E and E denied is equal to the impossible events. Therefore, the following relationship always applies. P of E is equal to 1 minus P of E denied. It is said that E and E denied constitute a partition of the sample space. Probability of the union of two events. In the particular case of incompatible events, the probability of the union of two events is given by probability of A union B is equal to probability of A plus probability of B. This is a special case. In the general case, instead, the probability of the union of two events is given by probability of the union of A and B is equal to probability of A plus probability of B minus probability of A intersection B. Conditional probability. The evaluation of a probability is based on a precise state of knowledge. If the state of knowledge changes, we are induced to revise our assessment. A change in information can be caused by information such the event A has occurred. The calculation of the probability of another event B must take place in the light of this new information. This probability, called conditional, is denoted as probability of B given A and expresses the probability of the occurrence of B once A has occurred. The occurrence of B once A has occurred implies the occurrence of both. Therefore, the probability of B given A is necessarily linked to that of intersection or concomitance A and B. So the rule for calculating the conditional probability of B given A, is the probability of an intersection divided by the probability of A, which is the new sample space. From the conditional probability rule, the composite probability rule is obtained. Probability of concomitance A and B is equal to the probability of B given A times probability of A equal to probability of A given B times probability of B. Stochastic independence. Two events are said to be stochastically independent if the occurrence of one does not change the probability of the occurrence of the other. P of A given B is equal to probability of A, or probability of B given A is equal to probability of B. In the case of S-independent events, the rule of compound probability leads to results that the probability of A intersection B is equal to probability of A times probability of B. That is, this applies only if and only if the two events A and B are stochastically independent. If one of the three equations applies, the two others apply. Bayes rule. This is the first Bayes rule, and in the simplest case, it is demonstrated as follows. Consider a sample space of an event C that we call cause, and we recall that C and C denied constitute a partition of the sample space. Let's also consider an event E that we call effect in the same sample space. Okay, so the effect E is this oval, which is green, depicted in green. It's easy to see that E intersection C and E intersection C denied are incompatible. Hence, the probability of E can be calculated as probability of A intersection C union A intersection C denied. This is equal to the probability of, since they are incompatible, as the sum of probability A intersection C and A intersection C denied. But both probabilities can be calculated using the compound probability rule. So they are equal to probability of A given C times probability of C plus probability of E given C denied times probability of C denied. Instead, if a partition of events, instead of a partition of events of the type C denied, we consider a partition of n events Ci, and we consider an event E in the same sample space, the absolute probability of the event E is equal to the summation from I, from 1 to n, of the probability of E given Ci times probability of Ci. The Bayes second rule is called Bayes theorem, inverts the natural logical flow, cause towards effect, allowing us to calculate the conditional probability of Cj given E of a special cause Cj, a particular cause Cj given the effect E. That is the probability that the cause has occurred conditional on the occurrence of the effect, so-called posterior probability of the cause. In the case of only one cause, the probability of C given E is equal to probability of E given C times probability of C divided by probability of E given C times probability of C plus probability of E given C denied times probability of C denied. In the terminology of the Bayes theorem, the probability of C is called the prior probability of the cause, while the conditional probabilities P of E given C and probability of E given C denied are called likelihoods. Application of Bayes theorem to the case of the Bayesian yacht tragedy. We can think that the sinking of the yacht is the effect E, and the possible cause C is a sabotage. In principle, we could initially assume that event C, the sabotage, is equiprobable to its negation. Probability of C is equal to probability of C denied is equal to 0.5. This is a prior hypothesis, and it is a neutral hypothesis. Based on what has been ascertained so far, it can be assumed that the sinking in the absence of sabotage is very unlikely. So we can assume that the probability of V given C denied is approximate 0. While on the basis of recent events, it can be assumed that the sinking as a result of sabotage is very likely. The probability of E given C is approximate to 1. Without affecting generality, for the purposes of the calculation, we can assume that the probability of E given C denied is equal to 0.1 and the probability of E given C is equal to 0.9. So on the basis of this assumption, by applying the Bayes theorem, we obtain that the probability of C given E, and here we repeat the general formula, and by replacing the numbers here, we obtain that the probability of C given E is equal to 0.9. The probability of C given E provides the posterior evaluation, that is after the effect sinking of the probability that has been sabotaged. As mentioned in the introduction, probability is based on a state of knowledge. Therefore, if the state of knowledge changes, the aforementioned evaluation can be also updated. In the graph below, I show how the posterior probability of C given E here, so the posterior probability of the cause, sabotage varies as the a priori probability varies. So the prior probability of the cause is here, leaving unchanged the two probabilities, the two likelihoods, probability of E given C denied and probability of E given C. It should be noted that even we start from a low prior probability of sabotage, 0.20, like here, then the probability of posterior probability of C given E, of the cause given the effect, is equal to 0.69. So it's rather high. Obviously, the red curve of the graph, while the starting point 0.00 and the ending point 1.1 remain fixed because the curve has to start from 0.0 and end at 1.1, will have a continuous trend depending on the values assumed for the likelihoods P of E given C denied and the probability of E given C. By changing these values in case of updates to the knowledge state, it will be possible to obtain an update of the posterior probability of sabotage. Thanks for your attention.
Allora, questa è un appendice di approfondimento al lavoro sull'applicazione del teorema di Bayes al caso del naufragio della nave Bayesian. Nell'applicazione del teorema di Bayes ho posto che la probabilità condizionata di affondamento dato non sabotaggio fosse molto bassa. In questa nota voglio spiegare per quale motivo ho dato questa valutazione. Innanzitutto ho scartato ogni ipotesi di affondamento per errori di progetto della nave, in quanto la nave era in navigazione già da molti anni ed aveva solcato mari ed oceani. Resta quindi l'ipotesi di una condizione meteorologica eccezionale che abbia influito sulla nave determinando una condizione di ribaltamento. Quali sono i motivi per cui ho ritenuto e ritengo tuttora improbabile questa situazione? In prossimità della nave Bayesian, come si vede anche da questa immagine, vi era un'altra imbarcazione abbastanza più piccola del Bayesian, una goletta dal nome Sir Robert Baden-Powell, la quale ha pienamente resistito all'evento atmosferico. Un video reso pubblico il giorno dopo l'evento, estratto da una videocamera di sorveglianza sul molo di Porticello, dal quale si vede chiaramente la nave Bayesian, non mostra un eccezionale evento atmosferico. Ciò si osserva anche dalle navi e dalle barche ormeggiate nel molo. Quindi da scartare l'ipotesi di downburst inizialmente formulata da alcuni. Anche altre videocamere di sorveglianza in prossimità del molo di Porticello hanno mostrato il manifestarsi di vento forte, ma non tale da potersi ritenere un evento di carattere eccezionale. Siccome si continua a ragionare sulle condizioni meteorologiche, ho ritenuto necessario approfondire questo aspetto basandomi su dati oggettivi. Quindi ho recuperato dati meteo da alcune stazioni meteorologiche ufficiali collocate in zone non molto lontane da Porticello ed ho estrapolato i dati della fascia oraria dalle ore 3 alle ore 5 del mattino del giorno 19 agosto 2024. Dati che sono nella gran parte cadenzati a frequenze di 60 secondi o leggermente inferiori. Limito la mia analisi alla velocità e alla direzione del vento e quindi passo a visualizzare un grafico nella slide successiva. Al momento non posso riportare i nomi delle stazioni meteo. Ho rappresentato graficamente le serie storiche dei dati in questo caso dei dati di velocità del vento e da esse ho fatto una serie di considerazioni. Una prima considerazione è che nella zona un po' più lontana dall'evento catastrofico, cioè nella zona di Palermo, la velocità del vento è stata molto più bassa rispetto alla zona di Porticello. Una seconda considerazione è che non molto lontano da Porticello, in una fascia oraria posteriore a quella dell'affondamento della nave, vi è stata una raffica di vento di particolare intensità. Questa raffica dovrebbe essere durata una decina di minuti. Questa potrebbe essere coerente con una raffica a Porticello nella fase di affondamento. Purtroppo nella zona più vicina a Porticello non ci sono dati ufficiali disponibili, a meno che io abbia ritrovato. C'è da considerare però una registrazione meteo nella zona di Solanto, quindi molto vicina a Porticello, da cui si evince un'intensità di vento massima di circa 40 nodi. Però si possono fare anche delle considerazioni di carattere orografico e quindi passo a visualizzare la slide successiva. Quel tratto di costa nei dintorni di Porticello, qui siamo a Porticello, è particolarmente protetto da venti provenienti in direzione sud-est, in quanto vi sono il monte Catalfano, questo rilievo montuoso, ed il capo Zafferano, che sono due rilievi montuosi piuttosto alti che proteggono il tratto di costa. Quindi potrebbe essere realistico pensare che questo flusso ventoso di durata comunque limitata, che ho rappresentato con questa freccia azzurra, ehm, ad una decina, limitato ad una decina di minuti, che in una zona più aperta è arrivata a intensità dei 60 nodi, nel tratto più protetto potrebbe essere stata più moderata, intorno ai 40 nodi. Una terza importante considerazione che ho evinto dall'analisi dei dati meteo ufficiali è che questa fase di raffica ha avuto come direzione prevalente la direzione sud-est, sud-sud-est. Ecco, questo è un aspetto molto importante che viene confermato dai tracciati AIS delle imbarcazioni Bayesian e Baden-Powell, che sono stati anch'essi pubblicati prontamente dopo la tragedia. E quindi passo a visualizzare la slide successiva. Questi tracciati sono riportati anche sull'interim report del MAIB pubblicato nel maggio del 2025. I due tracciati mostrano lo spostamento delle due imbarcazioni proprio nella direzione sud-est. Da tenere presente che questa mappa è correttamente, come quella precedente, è correttamente orientata con il nord in alto. Quindi i tracciati risposano a uno spostamento coerente con la direzione prevalente del vento forte che ha caratterizzato quella fascia oraria. C'è da aggiungere che le condizioni del mare erano invece di mare molto calmo, come si è visto anche nella prima slide, rimasto tale anche durante l'evento temporalesco e anche nel giorno successivo, per cui il mare non ha potuto influire in alcun modo rispetto diciamo, alla situazione che poi avrebbe determinato il ribaltamento della nave Bayesian. Quindi, seguendo il ragionamento dello spostamento dovuto al vento forte in direzione sud-est, si può ragionevolmente ritenere che l'imbarcazione si vada ad allineare alla direzione del vento, così come si allineerebbe alla linea della catena di ancoraggio al fondale. A questo punto noi avremo un vento che incide sull'albero, da considerare anche che le vele erano completamente assenti, eh, e quindi con la nave allineata rispetto al vento, e in questa condizione la possibilità di ribaltamento laterale sarebbe assolutamente da escludere. Nel maggio 2025 viene reso pubblico un video estratto dalle telecamere di videosorveglianza poste sull'albero stesso della nave Bayesian, e da queste immagini si può dedurre che nelle fasi immediatamente precedenti il ribaltamento, il vento incide sul tendalino non in direzione longitudinale della nave, ma nella direzione trasversale, cioè ortogonale alla direzione del vento. Se ne deduce quindi che in prossimità del ribaltamento la nave era ruotata di 90 gradi rispetto alla direzione del vento. Quindi se il vento va in questa direzione, la nave era ruotata pressoché di 90 gradi, quindi orientativamente in questa direzione. Questo elemento è estremamente importante in quanto è da ritenersi una forte anomalia, per quanto detto prima. Quindi in sostanza, dal mio approfondimento basato sui dati ufficiali di stazioni meteo, posso sinteticamente affermare che nelle fasi immediatamente precedenti l'affondamento vi è stata una raffica di vento in direzione sud-sud-est nella zona di Porticello. Questa raffica ha investito entrambe le imbarcazioni Bayesian e Baden-Powell, determinando lo spostamento nella direzione del vento. Questa raffica però non può essere essa stessa la causa del ribaltamento sulla fiancata destra, perché non spiega il motivo per cui l'imbarcazione si è oggettivamente trovata in posizione ortogonale al vento e quindi esponendo il fianco sinistro al vento. Raffica che di per sé potrebbe essere stata una condizione facilitante la rotazione della barca intorno all'asse di rollio, ma non sufficiente per portarla alle condizioni di ribaltamento. Pertanto concludo che le mie valutazioni di bassa probabilità di affondamento, dato non sabotaggio, sono estremamente basse. Confermo invece che sono elevate le probabilità di affondamento dato sabotaggio, su cui presenterò uno studio separato.
Greetings to all of you. This post follows on from the previous one I published about a month ago, in which I delved into the wind conditions in Porticello Bay on the night of August 18 to 19, 2024. This is because in my application of the Bayes theorem to the tragic sinking of the Bayesian ship, I initially assessed the probability of the ship sinking as very low in the absence of sabotage. To more carefully assess this delicate and crucial issue, I took inspiration from the ship's AIS tracking, an objective fact I personally learned a few months after the fateful accident, thanks to one of the videos by engineer Ugo Notaro, whom I want to thank once again for dedicating such close attention to the case. These reflections led me to decide to conduct some experiments to understand the phenomenology involved. Since it was impossible to conduct experiments with a full-scale vessel, especially one of that size, I decided to create a sort of simplified naval tank, a true experimental laboratory. The laboratory was constructed with a 150 times 200 centimeters PVC tank with a steel structure filled with water to a depth of 40 centimeters. I used a model sailing ship, very well made by a well-known German naval model company. It is 55 centimeters long with a 55 centimeters high mast. I developed a test plan according adopting several control factors to observe the vessel's behavior. In particular, I control the following factors: wind, speed and direction, initial position of the vessel, mobility of the anchor. In all experiments, the anchor was kept at the bow. The sails were furled around the mast. In this post, I provide some previews that will be better described and documented in subsequent articles. What I observed from experimental tests is that the starting position of the vessel when the gust begins has no bearing on the final position it reaches. After the initial moments, the vessel tends to align itself with the wind flow, with its bow against the wind, whether the vessel starts aligned or perpendicular to the wind flow. I also performed a further test with the vessel initially positioned with its stern against the wind, and the result was similar. I investigated whether there were differences between a lighted anchor, and therefore more free to move, and a locked anchor. And what I observed was that when the anchor is locked, the final position is reached more quickly, meaning the transition phase before reaching the steady state conditions is quicker. I observed that when the vessel reaches a steady state aligned with the wind flow, a rectilinear alternating motion is triggered relative to the anchor. This creates an unstable equilibrium between the forces at play. On one side, there is the weight of the chain, which tends to pull the vessel towards the anchor. On the other hand, there is the force of the wind, which, by pushing the vessel backward, determines the tension in the chain. Therefore, considering the inertia of the vessel's motion, even if the wind flow remained constant, equilibrium would never be reached. Another phenomenon observed in the experiments is that in a completely stationary situation, absence of wind flow and underwater currents, the equilibrium position of the chain is almost vertical toward the seabed, and the bow of the vessel is oriented towards the anchor. Another observation from these experiments is that even in the presence of a strong impulsive wind flow, simulated gust, the vessel never experiences a rolling motion, listing, but rather an immediate shift to seek a position aligned with the wind flow. In all experimental tests, the rudder was kept in the neutral position or aligned with the ship. Preliminary tests show that the rudder can have an effect on the ship's motion, depending on the wind. However, if the ship is anchored, it will still tend to assume a position aligned with the wind flow, even though this will take longer. Therefore, it has no significant effect on the positioning of the anchored vessel in strong winds. I also performed tests without anchor or chain, therefore with the vessel free and unrestrained, and the results were completely different, as in this situation the vessel tended to quickly turn and position itself with its stern against the wind. Thus, the vessel tended to move away quickly with the wind and as at its back. This is obviously a completely different behavior, consistent with the vessel's design and its fluid dynamics. Comparing the results of these tests with the AIS log of the Bayesian vessel, we can deduce that, as stated in a previous post, assuming a sudden gust, regardless of the vessel position at the onset of the gust, the vessel anchored by the bow, certainly found an equilibrium position aligned with the wind direction, south-southeast. This is the initial phase preceding the sinking phase. From the AIS log, it was possible to observe an initial phase of alternating motion, zigzag marks on the log. And this is consistent with the hypothesis of a medium intensity wind flow that caused the alternating motion observed in the experiments and described above to occur. Subsequently, the AIS log shows a very different behavior compared to this phase. This is the Bayesian sinking phase. I will provide details of this behavior in a later post based on further experimental tests already performed. However, I can certainly confirm and support the sabotage hypothesis.
Greetings and best wishes to everyone for a happy new year, filled with great hope for a true peace for all those affected by poverty and war. In this video, I present the latest analysis and the conclusions I have personally drawn from the Bayesian case, the disastrous sinking of a 55-meter long sailing vessel with a 75-meter high mast, which sank during the night between August 18th and 19th, 2024, off the Porticello Pier in the municipality of Santa Flavia, not far from Palermo. Let's briefly recap the three main works presented since October 2024. In the first work, I linked the sinking of the Bayesian to the Bayes rules of probability calculations, named after the scholar Thomas Bayes, of whom the owner of the sunken ship, the English billionaire Mike Lynch, was a profound connoisseur and admirer. Lynch died in the tragic sinking along with his 18-year-old daughter, four other guests, and a crew member. It should be remembered that a few months later, during the wreck rescue operations, another young life was also lost, of a high specialized technician. Therefore, we can say that this is a true tragedy. In the first presentation, I linked the sinking event to the hypothesis of a sabotage event, explaining all the details of the formula, the Bayes theorem, that led me to conclude that the posterior probability of a sabotage, given the sinking, was quite high. In the following months, further information was gathered, further analysis, reasonings, and investigations were conducted, some of which obviously were and are covered by confidentiality due to an ongoing legal case. Those who, like myself, were passionate about the story were able to follow these steps. And thus, I arrived at the second video I posted in October 2025, in which I attempted to explain whether there had indeed been a particular severe meteorological event affecting Porticello Bay that could have struck the Bayesian vessel. From my findings, I was able to ascertain that there were fairly strong gusts of wind that night, but they most likely did not exceed 40 knots. This fact prompted me to further investigate the ship's behavior in the presence of wind, where the vessel is anchored by the bow. So in the third video, which I posted in November 2025, I showed the results of a series of experimental tests conducted using a statistical approach aimed at understanding the effect of certain factors, including wind, on a vessel anchored at the bow, simulating the Bayesian vessel. From this study, I drew a series of conclusions, which I described in the video, including the definitive exclusion that the sinking was due to the ship listing, itself caused by strong winds. Therefore, at this point, I focus on the last aspect of the Bayes theorem to be explored, namely the probability of sinking given sabotage. What is the probability of sinking given sabotage. So at this point, I made some physical considerations and hypothesized a specific situation that I will gradually describe in this presentation. In this slide, I show the model of the vessel anchored to the bow and hypothesize a three-dimensional Cartesian reference system obtained by crossing three orthogonal planes. The first xy plane is horizontal plane, let's say parallel to the deck of the vessel. The second plane is an xz plane, let's say vertical, orthogonal to the xy plane and parallel to the mast. The third plane is a plane orthogonal to the first two, which passes through the mast of the vessel. In this image, we can see the three planes and the Cartesian reference system with the x, y, and z axis. So the x-axis is the longitudinal axis of the ship, the y-axis is the transverse axis, and the z-axis is a vertical axis, let's say parallel to the mast. Having defined this reference system, in this slide I show a force F1 that pushes the vessel mast toward a point I call G, which we could view as the center of gravity of the surface on which a hypothetical aerodynamic force due to wind acts, because we know that the wind and therefore the fluid mass acts on the mast and in part also on the hull of the vessel. This thrust due to the distributed air mass can be thought of as equivalent to a force concentrated on a point we can call the center of gravity of the aerodynamic thrust. I have called F1 this force concentrated at point G, and now I see that this force F1 could cause, if there were no other forces, the rotation of the vessel around a point I call M, the so-called metacenter. Therefore, the force F1 acting on point G generates a healing moment around the metacenter M. What is the force F2? The force F2 is the force I would use if, instead of positioning the force at point G, I positioned it at the top end of the mast, or at the point I've called it T. Physics teaches us that if I want to obtain the same moment, the product F2 times H2 must equal the product F1 times H1. So that since H2 is approximately twice the height H1, the force F2 is approximately half the force F1. Simply put, I can achieve the same rotation effect around the metacenter if, instead of having a force F1 acting on G, I have a force acting on the end of the mast equal to approximately half the force required to achieve rotation due to the wind. At this point, I make this argument. If I know the aerodynamic forces required to achieve rotation, causing the ship to heel by an angle equal to that which would cause it to sink, I can imagine achieving the same result using a force equal to half that due to the wind, but applied to the tip of the mast. So at this point, let's move on to this slide and begin to better understand what can realistically be imagined. We can imagine that a tensile force applied to the point T could be obtained thanks to a rope applied to point T, starting from a point P, which could be a point on land or on the coastline. This rope will be a rope of length, let's say L. In this diagram, I call D the horizontal distance between the fixed point P and the boat. This is not a perfect diagram that will be refined in greater detail, or not necessary here. I then call the H the height. It's not the height of the mast alone, but the overall height of the mast plus a small portion below it. I call alpha the angle between this horizontal segment of length D and the segment of length L. The so-called pull force has its horizontal component the force F2, seen in the previous slide, while the vertical component of pull is largely counterbalanced by the Archimedean thrust. Doing some simple calculations, assuming the boat is approximately 35 meters distant from the closest point on the land, and the total height h approximately 80 meters, applying the Pythagorean theorem yields a rope length of about 359 meters. At this point, knowing the force F2, which I need to rotate the boat, by calculating the ratio between F2 and the cosine of alpha, I obtain the magnitude of the pull force. Knowing the pull force, I need a rope with a braking load greater than this force to pull the mast from the end T. By doing some calculation, which I omit here, I found that a good synthetic rope with a diameter of 12 millimeters is sufficient to satisfy the required constraint. At this point, let's see what happens on the other coordinate plane, namely the XY plane. I hypothesized and represented the boat with the anchor blocked, represented by point O in the diagram. On the XY coordinate plane, the pull force component, together with the reaction on the chain, generates a moment that causes the ship to rotate. From the diagram, we can predict a counterclockwise rotation of the ship. Therefore, with the bow moving to the left, I can anticipate, but I won't explain here, that based on the relative positions of O and P, a rotation could also occur in the other direction, therefore also clockwise, still producing the same final effect I will describe soon. Having made this schematization of forces, at this point I asked myself if I could observe this phenomenon experimentally. So, using the experimental setup described in the previous video, I created a simulation I showed a video in which the model boat with the anchor blocked is subjected to a force of the type described before. This video shows the final effect. It should be noted that the model boat does not sink because it is closed on top. A real boat, however, like the Bayesian, in that configuration, being open at the top, would quickly fill with water, losing its Archimedean buoyancy, and would inevitably sink. At this point, I can draw the conclusions of Bayes' theorem applied to the case of the sinking of the Bayesian ship. We had therefore said that the formula of Bayes' theorem in this case was as follows. P of C given E is equal to P of E given C times probability of C divided by the same P of E given C times probability of C plus probability of E given C negated times probability of C negated, where E is the effect, that is the sinking, and C is the cause, that is sabotage. So at this point, we can say that probability of E given C negated, this one, is equal to 0. That is, we can say that it is impossible for the Bayesian to have sunk due to a strong gust of wind. Therefore, in the formula, the second term in the denominator cancels out. So this is 0, and so all the second term is 0. Leaving a denominator equal to the numerator, which would lead us to conclude that the probability of sabotage given sinking is equal to 1. Note that, before taking this step, we must exclude the possibility that the other conditional probability is also 0. The probability of sinking a given sabotage must be different from 0. Now, having been able to demonstrate, also using experimental results, that sabotage resulting in sinking using the described technique is absolutely possible and realistic, I can certainly set the probability of E given C to be different from 0. And it is also a very high probability, we can say. Therefore, whatever the prior probability of sabotage, applying Bayes' theorem, the probability of sabotage given sinking is equal to 1. In conclusion, we can say that it is mathematically proven that there was sabotage that resulted in the sinking of the Bayesian. Thanks for your attention.